All right, so here's part 2 of DNA replication. We're going to look at the lagging strand or the bottom strand now. So where we left off was we looked at what happens in the leading strand. Maybe you want to highlight this word and just know that it's the new DNA. I drew it as green. So we finished off this. Leading strand is built towards the replication fork. So what we need to do now is the lagging strand. It's actually built away from the fork and built in smaller chunks called Okazaki fragments. So some things we need to remember are that primers are needed. So let's say that if we go back in time and wind up this area and pretend that the replication fork started here or something, let's say we have a primer around here. Primase laid it down. I'm not going to draw primase in there, but we know that primase lays down primers. And now let's start going back to the 5' 3' thing. Let's go to the template strand on the other side. So we had 5' here. That means that the opposite strand must have had a hydroxyl hanging off of it, and a hydroxyl is the 3' end. So if we follow that through like this, and we go to the end and we see that this must be where there's a phosphate, or we call it the 5' end. If that's the case, note that every single piece of the DNA has a 5' and 3' end because every single nucleotide, whether it's a ribonucleotide or deoxyribonucleotide, has a 5' and 3' end. It will always have a phosphate on the 5' and a hydroxyl hanging off the 3'. And so we know that the new strands are always anti-parallel. So that means if this is 5', this is 3', and this ends 5'. Okay, so the other thing that we need to remember that's really important is that DNA polymerase 3, and I think we forgot a 3 up here, it's a Roman numeral 3. DNA polymerase 3 can only build in what direction? It only builds in the 5' to 3' direction, and it needs a primer to do that. So the built strand is the new strand, so that's going actually this way, which is the opposite of the leading strand. All the principles are the same. It's just that because of the directionality of this whole thing, the overall building is going to happen, in this case, to the right. And so what we end up with, this is our new strand, which will continue on. This whole thing was built by, we'll draw at least one of them, built by DNA polymerase 3. And again, it can only build in the 5' to 3' direction. So it will be building this way. But notice that, what about all of this? We still have the replication fork opening to the left. And so what happens is we have kind of a 2 steps forward, 1 step back kind of idea that we're going to have to lay another primer as the replication fork opens. So let's say something like here. There's another primer laid down by primase. And DNA polymerase 3 comes through and it fills it in with DNA. So what you end up with is these little chunks. You have more than one primer that's needed, and you end up with these sections. And that's what we mean by an Okazaki fragment. So one of these guys, Okazaki, is the Japanese scientist, I believe, who found out about these. You have these Okazaki fragments. So as the replication fork continues to open, you end up with more and more of these fragments. That's what makes it a little bit more complicated than the leading strand. So this is called lagging strand, the lagging strand. So you need a lot more DNA polymerase 3s working, you need a lot more primases working on that side. All right, number 6, DNA polymerase 1. That's why writing the 3 was important, because now we have another DNA polymerase. Excises the primers, means it takes out primers because we know that primers are made of RNA, and we can't have a complete new daughter strand that somehow has a little bit of RNA in it. That doesn't make sense. So we need to replace the RNA and put DNA in instead. Now, this is not shown, and in animations that you might see, it might be shown, but it's kind of difficult to show it in a diagram that's just a snapshot, so that's not going to be shown. Another enzyme, DNA ligase, joins the gaps between Okazaki fragments. So once you take out the primers, there's gaps in the sugar phosphate backbone. And so you want to make sure that those gaps are cleaned up and put together so that you have a double helix that is cohesive and put together properly. DNA polymerase 1 and 3, proofread. So DNA polymerase 3 actually has a double job. It not only builds the new strand, but it also proofreads. And they also correct. So what that means is that if there's an incorrect matching, so we know the matching rules are here. If an A accidentally matched with a G, for example, then DNA polymerase 1 and 3 go through and can actually take out the wrong nucleotide and put in the right one, which is insanely cool and an example of God's awesome design, how it's not, this already is quite complicated, lots of things going on, but the fact that it can be proofread and double checked for errors is quite something. And if you think of all of what you know about DNA mutations and how sometimes just one thing going wrong, one nucleotide that's wrong, or one amino acid that ends up being wrong means that you can have a disease that could even be deathly, even be fatal. So this proofreading is a pretty cool part of this whole process. So there you go. There will be some videos and some other tutorials, things like that, just to go over this one more time, or a few more times is probably best. And let me know if you have any questions.